Good morning to all of you. So, in the last class, we had discussed the line shapes. You remember how uh, the splitting pattern and the line shapes. That was this one. So, that was due to the the different electronic environment along different directions, interactions happening. If they are different, then you can have this kind of asymmetry arising in the peak profile, which was discussed in the last two classes, I think. Yeah, so today moving forward, we are going to we also discussed, you remember the pros and cons of the derivative spectrum. There was then splitting pattern, and I told you that whenever you draw, remember what I am talking about is that if you draw the splitting pattern, the intensity should also be divided into the two components, that so gradually reducing. So this divided into three, so you see the intensity, look at the intensity how it decreases. If this signal is divided into four, the intensity will further drop for individual each of these. So this is a care that you have to take in care you have to take while drawing these pictures. Okay, so in stick model, the way you represent here by three lines, four lines, so accordingly that's the intensity, and this is another point that you have to take into account. So now we can move ahead with so these were the cases that we discussed for different g. So g values that was there for perpendicular direction, parallel to the magnetic field, or perpendicular to the magnetic field, and the g values, if they are not much different, that happened here. So they appear as a congested section in a EPR spectrum. So you see it is a congested part of the EPR spectrum where so you can see here there's 1 2 3 4 5 6 7 8. So that's how. So I is equal to 7 by 2, so the interaction giving you this kind of thing. So you also remember that we have, this is the interaction with the nucleus, hyperfine and we call it hyperfine interaction. In one of the cases I also discussed the super hyperfine interactions. What was that? Interaction of electron with the same nucleus of the same atom is hyperfine interaction. फॉर एग्जाम्पल इन दिस केस द मेटल एटम, उसके न्यूक्लियस के साथ इंटरेक्शन हो रहा है तो हाइपर फाइन इंटरेक्शन कहलाएगा। लेकिन जब यही इलेक्ट्रॉन इंटरेक्ट कर रहा है बगल में जो लिगेंड है, नाइट्रोजन एटम है, ऑक्सीजन एटम है, उसमें से किसी के न्यूक्लियस के साथ इंटरेक्ट करता है, दैट इज सुपर हाइपर फाइन इंटरेक्शन. So typically, if you remember, there was case of nitrogen group appearing, and in that case there was super hyperfine interactions. So that both these things can happen, hyperfine, super hyperfine interactions. And then the next thing is that interaction that can happen between, so there's one electron interacting with nucleus of different, either same atom or the other atom, which in case of a metal ligand complex becomes the ligand nucleus of a ligand atom. So these were the two things. Now the third thing that we are going to discuss is the, if you have more than one electrons in that particular atom that we are talking about. So hyperfine interaction, so the interactions would be different. This time it would be the electrons interacting with electrons, and so we have to discuss in terms of multiplicity. So that's spin equal to n by 2 have some special characteristics, and that feature we are going to discuss. And such so greater than, if there's multiplicity, so spin multiplicity, what does it mean? I told you what a meaning of multiplicity, if you remember my quantum mechanics classes, that you have that many orientations possible for in a three-dimensional space you can have so if 2s plus 1 is the number of orientations of the angular momentum spin angular momentum vector that is possible. So it initially for one electron is a plus half minus half, right? So either z component is aligned or z component is opposed to the uh, this magnetic field like that, or along the z-axis. There was two components possible quantum mechanically. Now you can have many more when the such interactions occur, and spin coupling, spin orbit coupling that we have already discussed in previous classes. So because of that kind of situation, you have spin multiplets. Different spin levels are created, which are called spin multiplets. And for particularly the high spins having s greater than 1 systems, there is a interaction that happens between individual unpaired electrons. Okay, so because uh, an electron with spin will have a magnetic moment. There is another unpaired electron with spin, and as I told you, spin is always there for any electron, whether it is a part of atom or not. Okay, so whenever two electrons are present, they are interacting. So they will have a magnetic interaction. So even if you do not apply any magnetic field externally, each one of them is behaving as a tiny magnet, and so there will be interaction. And this interaction we call it as zero field interaction, right? Two electrons. So we are talking about systems where n is greater than uh, S is capital S, the multiplicity is greater than this thing, n is greater than 1. So in all these cases, you will have, when we talk about Zeeman interaction is with the external magnetic field that splits the energy levels. And this one, energy levels of this, depending on this Z component that is possible. And then this is another interaction that is always present, which is called zero field interaction. ठीक है. So दो इलेक्ट्रॉन है, दोनों एक टाइनी मैग्नेट की तरह बिहेव कर रहा है, दोनों अनपेयर्ड है और एक ही एटम पे अगर लाई कर रहा है, तो यू विल ऑलवेज हैव सच इंटरेक्शन पॉसिबल, which is called zero field interactions. uh, and this interaction is much stronger as compared to Zeeman interaction. So external field, so this is zero field interaction. So this is, we are talking about two electrons, two or more. I mean, just to give you an example, I am writing uh, electrons interaction. So electron interacts with electron. This is what I am talking about, electron, and each one of them is behaving as a tiny magnet. This is what I am saying, right? Each spinning, any electron has a spin, and because of the spin, it will have magnetic moment. So a magnetic moment is a property of a magnet, a small magnet, a magnetic dipole. I told you that electron is also a magnetic dipole. So that's how interaction happens, and particularly so is greater than one system, and this particular interaction leads to a splitting that we will see, and that splitting is much larger than the splitting obtained when the field is applied. So such systems, what we know, what we call them is that a special name is given to them, Kramer's system, whenever S is equal to n by 2. So always greater than 1, I already told you that we are discussing this in context of that. So 3 by 2, 5 by 2, etc. If you have, that is called Kramer's system, half integer systems. And as opposed to that, you can also have integer systems or non-Kramer systems. So what happens is that there is a splitting of energy levels, plus minus half, plus minus 3 by 2. These two spin levels will be remain degenerate, and 3 by 2 level will be different, lying higher in energy 5 by 2, like that, plus minus 5, and so on. So that will be clearer when we see this picture in the next slide. That is, where is it? Yeah, here. Sorry, it's here. I should have put it there right away, but yeah. So this is what we are talking about. You have, in absence of anything, this is the uh, 5 uh, d orbitals. uh, so this is, sorry, this is a system that we define for, depending on group theory, that you have when you have totally symmetric environment, spherically symmetric, nothing. So in absence of any magnetic field, anything, you have this kind of splitting happens. So this particular thing is for um, plus minus. So these are degenerate sets. This is plus minus half, plus minus 3 by 2, plus minus 5 by 2. So this is the, and this d is the uh, what we call the splitting parameter, zero field. So this is what we call as zero field splitting parameter. Splitting, okay. So this is 2d 4d. So this splitting is much more than the energy h mu, the energy of the convention, normally the wavelength, that microwave wavelength that is used, microwave frequency that is used, as compared to that, it is always much larger, the d separation that we are talking about. And then the second scenario is that after that, we are, when we apply magnetic field, and as the magnetic field increases, b not increasing, then accordingly you can have the splitting. Then these two degenerate sets become non-degenerates, and there is a splitting between this. So you can expect transitions between each of these pairs, the uh, plus half, minus half to plus half, and like that, you will always have this kind of transition. So each pairs, so these, each of these are called Kramer pairs. And now when you apply magnetic field, there's the degeneracy is lifted, and none of them are crossing. You can see that because the splitting, initial splitting, the zero field splitting is so high, and the microwave frequency is less. So these splitted lines do not cross each other. They will never, like, it will never happen. This crossing will not, doesn't happen in a Kramer system. Okay, so there is no crossover points obtained in such Kramer systems. The two, plus half minus half, they split up, degeneracy is lifted, and the transition, providing sufficient energy of, you can have the spin transition, one spin state to other spin state transition can happen within the Kramer pairs. So that's what is indicated by these arrows. uh, and of course it will depend. If you increase the magnetic field, this will happen like this. It will go on increasing the energy requirement. So this is what is called a Kramer pairs, multiplet spin half integer. The sub levels of the half integer multiplets, groups, they are grouping in pairs in the zero field when there is no field. And this is, all these things are intense quantum mechanical treatment, but I'm not going into that at this moment. We are concerned with how we apply in systems to understand. So the let's get the idea what happens in the systems like this. So this, what we, in shorthand notation, we express this as zero field splittings. That's what, and the splitting factor, ZFS splitting factor, is that D, indicated by capital D. And that's what we were looking at, the Fe3 plus, high spin Fe3 plus, which is D is equal to, sorry, S is equal to 5 by 2, capital S is 5 by 2. So that's what, and this kind of system, which is found in many cases, high spin cysteine residues in redoxin. Naturally, you find in a heme group where it is also attached to cysteine residues, and this was the example of that one that I just discussed. And it is important to note here, these are the Kramer doublets. So each one of them are called Kramer doublets that we have obtained in the spectrum. When we analyze spectrum, we will get three peaks, each corresponding to the transition between the Kramer pairs, right? And so that, as shown in the picture, look at the picture, the separation is much larger than the splitting caused by the magnetic field B naught. Okay, so that is typically so these are the points that you take care if you are drawing such thing, showing somewhere. uh, so doublets are labeled with the quantum number ms that we had done already. The doublets, however, so they in fact are linear combinations of two different levels. So this was initially when I was talking in semester 2 when we were discussing spin uh, spin yeah wave functions. At that time I told you the alpha beta, it is a combination of that is which in case of more than one electron that exists, that is the real situation that we define. So in a similar way this comes out to be a linear combination, just like a linear combination of several wave functions. If two as if two wave functions are combining, you will get two additional two new set of combinations. So similarly you have this arising due to that. Okay, but so degeneracy is lifted and already discussed this point. uh, Within each pairs, split pairs, you have transitions that we can observe. uh, so each what so in other words, so as I told you, there is no crossing over, no mixing of energy levels. There is each Kramer's pair give rise to its own resonance. So these are the points to with respect to the figure that we have in the previous slide. So there is no crossing over, that I told you. And then we we can expect that there will be g values will there will be one effective g values to define this transition. And this effective g values, this beta is the Bohr magneton and b is the magnetic field required for the resonance to be achieved. So this g effective is the it has all the g values, real g values, and what else, the zero field interaction. So g, as we understand now, uh, in the as discussed in previous classes, we understand the G in much detail, and the components parallel, perpendicular, all that. So in addition to that, there is additional component that gets added up, which is the zero field interaction, and to give you the G effective. So the zero field interaction parameter is just like the G values were anisotropic. So this interaction can also be anisotropic. That means that you can have along x and y and z axis, you can have different types of interactions. And so to define that, to develop a framework for understanding that thing, we have a system in place. G A is the small a we represented initially. So A is for hyperfine interaction, G is the as I told you, it was a relativistic thing, a G factor coming up, and that change with the immediate surroundings. So these are independent, are not sorry not independent, they can be related to each other. The zero field interactions in the different direction x y z are defined through this splitting parameters dx dy dz, and their combination obeys this uh, equation. So they are also related to each other in this two through this equation. So the component along z is 3 by 2 dz. This is called d, capital D, denoted by d. And we also define another term E, capital E, that is dx minus dy by 2. So when you have, so the d is the splitting parameter along x, dx, dy is the splitting parameter, zero field splitting, ZFS splitting parameter along, and this we used to define a term which is called rhombicity, which is E by D, represented by rho. So rho is the symbol of rhombicity, and which is defined by E by D, with this rho varying between yeah rhombicity is, so this is the, sorry, this is eta, not rho, eta varying between 0 to 1 by 3. So we have already discussed that zero field interaction is much bigger than the Zeeman interaction. Okay, and we have gx, gy, gz as a separate component of g along x, y, and z. And suppose if gx, gy are fixed at 2, then what will be the shape of the spectrum effective g values when we have such interactions? So then it is, if gx, gy, gz are fixed, and then we only consider the effect of these splitting parameters, then it is the rhombicity, it is the only the function of rhombicity that the response, when you place in the external magnetic field, the all these EPR transition will be a function of uh, rhombicity and so the g effective g value can be that can be related to the effective g values, and the relationship is understood through a graph which is called as rhombograms. You know, right, that's यहाँ पे कट जा रहा है नीचे slide show how, okay, so that is something, yeah. So the rhombogram, so typical rhombogram is drawn for which is on the next slide for s is equal to 5 by 2 system. So this is a typically what we call a rhombogram. Each कट क्यों रहा है? हाँ, थोड़ा सा ऊपर कर देता हूँ. So this is what we call as rhombo, एक minute, E by D. Let me just stretch it. Yeah, now it's okay. Huh. So it is on x-axis you have E by D plotted, and on y-axis you have the g values. So what are these? So for all of these three pairs, so we are keeping our focus on this 5 unpaired electrons system. So s is equal to 5 by 2, and so each of these, for each of these Kramer pairs, 1 by 2, 3 by 2, 5 by 2, we can have three different values of g due to the ZFS interaction, zero field splitting, happening in differently along x, y, and z. And so that we have defined the x, y, z factor, E by D rhombicity we have already defined, and so we can plot three lines for each of these pairs representing the variation in the g values for the each of the Kramer's doublet that is obtained in the spectrum. So this is, so each of these pairs can have three different values. So this is what we have. So the plotting here you see is the g value. So this is g along y-axis and E by D on the x-axis. Okay, so the analysis of this, so the spectral analysis now is becomes simpler if you have a rhombogram and then they are analyzed. So for if you have plotted E by D and corresponding g values for all such combinations, then it becomes easier. You simply, as per your observation, you can calculate the g value from the spectrum directly. Now it arises for what kind of transitions that you can understand by placing just a scale, a ruler, parallel to the vertical axis. So and find the where it matches the observed experimental G values. So if you do that, then it becomes on the next slide I will show how you do that. uh, so the, but so you can account for all the G values by looking at it through this diagram, but there are certain limitations for X band spectrometers, where the magnetic field generated by these magnets is 1 Tesla, and so it is below G is equal to 6, you cannot detect it. So this gets if it is if G value falls below this value, then it remains undetected uh, experimentally. Undetected, it will remain undetected below 0.6. So uh, so the intensity, so of course, because if the G is anisotropic, intensity will be spread over a larger region, and so we have if the G value is the anisotropy is less, then the spectrum will be not spread over a wide range. Mm, so and the best case scenario is that when all the three coincide, all the G values coincide, so you can see it happening over here, or yeah, all the three coinciding here in only this diagram, not in all cases. So this is clearly we can identify in plus minus 3 by 2 doublet the dombogram for this, for S is equal to, so these are all for S is equal to 5 by 2. We have three Kramer doublets for S is equal to 5 by 2 system, and at an E by 2 E by D of 1 by 3, you can see here the scale is not visible. That's a problem. I must have reduced it further. Okay, so अब दिखेगा. Yeah, so you can see here that this particular thing is matching happens at what value of X? 0.33. So that's what is written over here, that E by D of 1 by 3 gives this particular uh, G value of 4.3, where all the X, Y, Z along the three directions, the G values are equal, effective G values are equal. So taking into account all these ZFS interactions, also they are coming out to be equal. So this is a typical line for Fe3 plus that is observed in Fe3 plus case. Um, so different temperatures, you can have different doublets will be populated. So you can record the spectrum at different temperatures to fully characterize the system. Uh, and which one will be more populated? Lowest energy, yes, lowest energy. So lowest measuring temperature, uh, you can still have so when the so in most more than one doublet will be occupied at lowest measuring temperature, because the energy separation is low. So if you are comparing room temperature and things like that, most of the doublets, Kramer doublets are occupied, that spin states are occupied. And also when you have D is positive, doublet is the plus minus half is the lowest one lying in energy, in terms of energy, whereas if D is negative, then it will be reversed. So this is the application of what I was telling you. You have to put the ruler. So this red line represents the ruler. This particular red line in the spectrum here is the ruler. This is the typical spectrum that is obtained. Experimentally observed thing is this EPR spectrum for Fe3 plus in ruby redoxin. This is a protein in some bacteria. So what you observe here is that a very good intense line at which you can calculate, very easily calculate the G value, which is 4.32. And also if you zoom up, if you zoom in here, you will also find there is another peak appearing at this particular field value, which gives you G value of 9.63. Now, when theoretically, if you have rhombogram is prepared for uh, S is equal to 5 by 2 system containing all the Kramer doublets, so plus half minus half, 1 2 3, so 3 rhombograms available for. Then you try to match this experimental value on this in this figure, where you are getting this 4.3 for all of them. So you are appearing somewhere here, you are having this, where, and 9.63, where you are getting that, you are getting it here. So this one is 9.63 appearing over here, 4.32 something somewhere here. So at this point, uh, if you take this red ruler and move it left or right at any other point, it will not match these experimental details. So we are now able to find out the E by D values for the transitions that has been observed by simply putting the ruler around it on this rhombograms for all this. So the G values that it arises, so it can be easily located through this. So the main feature, so this is measured 4.5 Kelvin, the very isotropic looking. So isotropic looking peak at 4.32, this is what we obtained. And this zoomed in view gives you the blow up or zoomed in view is here, shows up 9.63. That's what, and the red line we saw in the previous picture, this red dashed line is your the ruler that I talked about earlier. So this is your ruler, and you just move it left right and find where you are getting all these things matched up, where it is matching with experimental details. So that one is your E by D value. This happens at E by D of 3.315, where you can talk about 9.63 peak is due to the plus minus half doublet, Kramer doublet, and 4.32 peak is due to, so this one is due to plus minus half Kramer system doublet. This one is this is due to the plus minus 3 by 2 Kramer doublet. So this is how we interpret it. Okay, just a moment. So sorry for. Okay, so we were here. Um, So this was the Kramer doublet that I told you. So clearly this one correspondence we get in the previous diagram, as we showed, 0.315 corresponds to 9.63, and clearly we are getting that. We can also see that 4.32, this happens here, and so almost all things are matching up when the ruler is red dotted dash line is placed like that. And so we conclude that this is the E by D values for all of them, all these things that we have. So S is equal to 5 by 2 system having E by D of 0.315, that is the rhombicity that we define. And so we can account for the each of the W plus minus half system or plus minus 3 by 2 system. Okay, and similar thing sometimes it gets yeah, this is a rather complicated spectrum for Fe3 plus in catalase peroxidase CatG enzyme, but anyway, so here it is a combination of two. So this is the observed spectrum that you see in the top panel, and the two given below are the simulated computer generated thing, considering that the at certain two different types of interaction are occurring. Again, it is the ruler thing that is used. Ruler, if the ruler is used, that tells us that there are two separate thing that happens. So lowest g values you are obtaining 1.9 around 2, highest g value 6.63 is obtained over here. So there are four in the original spectrum, there are four different g values being obtained. That indicates that you may have different types of interactions happening. Lowest g value at 1.99 and highest at 6.63. So this kind of complex spectrum appears sometimes when you have two species are present with different rhombicity. So this kind of thing is so uh, so as I told you, the top two in the previous diagram, top two. So this one, the black and blue, is the observed spectrum that we are talking about. Simulation of the original data, black line, and the blue one was the combination of the two simulated images given at the bottom. So two different rhombicity that we are talking about, if we have to find, then the first component we can see that it is at when rhombicity is 0. At this point you can get this particular value of 6 is coming over here. Yeah, you can get this value of 6 point something. So that is possible here. So you are getting that. So that is the plus minus half doublet when you are having that thing. So this is happening at e by d 0 when rhombicity is 0. And the other component that you will observe is that happens for that this the second red line that you see, it matches up for plus minus. So you can see two different values over here for two. You are getting so two values for 2 plus, so 1 2 3 4, four different g values, and four g values you can account for 1 2. So 1 2, and here you are getting 3 4. That, so the two systems. So 0.03, same is true for second component, but now the spectrum is having some more rhombicity, that is the value is more positive, rhombicity is positive, and this gives rise to, and this value you can why you are getting the g is equal to 2, that can be accounted for. So uh, so so there is also a limit. Now in the last part we are talking about the g is dependent on the spin system, but there is a highest that we can obtain for s is equal to half system is 4. Similarly, you can also think of when you have different is like s is equal to 3 by 2 system, highest g value is 6. So there is a limit to what g can be achieved for different spin systems. S is equal to 5 by 2, maximum g value that can be obtained is 10, and like that. So s is equal to 7 by 2, you have 14, s 9 by 2, so it is 18. So what you are getting, 2 s plus 1 kind of thing is coming here. So that's all for this part on Kramer systems. In the next class we can start now photoelectron spectroscopy. So I'll stop here.